Hello, everyone. Once again, thank you so much for your time. Today, I'd like to continue on our discussion on EMC consideration. Our topic for today's discussion is on the far-field radiation, specifically on common mode radiation. Okay, so this part 18 series, we are going to concentrate on common mode radiation. On the previous video, which is part 17, we actually focused on differential mode radiation. So if you are keen, okay, please look at the part 17 series discussion on EMC in order to fully understand this differential and common mode under far-field radiation. Okay, the rest of the EMC video, I have also put the link under the description. So please go through the video if you want to know more about EMC. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to help this channel by like and subscribe. Guys, we need the like and subscribe in order to improve the service of this channel. Thank you so much, guys. I really appreciate your effort. What is common mode radiation? In short, common mode radiation is the result of undesired voltage drop in the circuit cause some part of the circuit to be at a common mode potential above the true ground plane. Okay, so what does this sentences means? Okay, take a look on this diagram here. So this is a patch of ground plane. Okay, if you take a closer look, this is actually where the actual ground is. And at the other end of the ground plane, okay, these two may have some potential difference. In reality, okay, when at this ground plane, actually they don't have an identical voltage. And this point is actually much higher as compared to the actual ground. And because of the potential difference, it actually creates a ground voltage. Next, common mode radiation can be modeled as a short, less than a quarter wavelength, monopole antenna. Okay, so this monopole antenna can be the cable or PCB track that is driven by a voltage, ground voltage, Vn. Okay, so this is what it means. For example, at the other end of this ground, this can be a cable or PCB track, which is linked to another device. So this cable and PCB track can potentially become a monopole antenna. And basically they radiate out, okay, which is called common mode radiation. Okay, the diagram is actually represented on the right. So this is the difference between the two ground points, which create a ground voltage, which is denoted by Vn, which is illustrated here. So this is the cable or PCB track that is linked from the ground plane to another component. Okay, so this thing can be potentially become a monopole antenna, and basically this is how common mode radiation actually occur. Okay, common mode radiation, okay, they are actually much harder to control as compared to differential mode radiation. And normally, okay, it actually determines the overall radiated emission performance of the product. Okay, so in differential mode radiation, if you recall, how can we reduce the differential mode radiation? We can actually keep the area as small as possible. So we actually can minimize or we can actually control the differential mode radiation. However, for common mode, okay, it may be much harder to control because you can see here the potential difference between the 2 points, which is very difficult to cancel away this ground voltage. Hence, because of this, common mode radiation, typically they are much more harder to control, and they actually are the main culprit that generate the radiated emission. Okay, for a short antenna of length L over a ground plane, okay, the electric field strength measured at a distance R in the far field, okay, can be calculated by this formula here. Okay, later on, I'm going to give you two examples how to calculate the common mode radiation. Okay, so the E is in terms of V over M, F in terms of Hertz, I in ampere, and the length and the distance of observance in meter. Let's quickly do one example. Okay, so calculate the radiated emission of common mode at a distance of 3 meters with the DUT operate in a frequency of 90 megahertz with the antenna length of 1.2 meter and current flow of 2 microampere. Okay, so this is the equation that I shared with you on the previous slides over here. Okay, so what you need to do is you substitute all the parameters here. So this is intact. Okay, frequency is 90 megahertz. So this is where is the 90 megahertz. Current is 2 microampere, okay, which is here, 2 microampere. The length of the cable is 1.2 meter over here. So we punch the calculator. Okay, we can calculate the common mode radiation is equals to 90.432 microvolt per meter. Okay, next example. Okay, we normally want to calculate, okay, what is the length that we can permit in order to compliant to a certain standard. Okay, so for this case here, okay, we calculate how long is the length of the cable can we afford in order to compliant to this FCC class A. Okay, so this is the equation that we have compute earlier on. Okay, so the key idea is we need to know the length. How long is the length? So I need to make this as a subject over here. So how can I get this length? So this E multiplied by R, which is shown over here. So this 4 pi is equal to 12.6, okay, multiplied by 10 minus 7. So I have the frequency, okay, and I also have the length. Okay, so this sine theta normally we would ignore. Okay, so I have this equation. So what I need to do is I substitute the parameters. This FCC class A, okay, the maximum permit is 300 microvolt per meter. Okay, so this is where 300 microvolt per meter. This is the point of observance, okay, which is 3 meter. Okay, so divided by, this is 12.6 over here. The frequency is 94 megahertz. The current, how can we find the current? Okay, this is the voltage. This is the resistance. Okay, current is equals to the voltage divided by the resistance, which will give us 125 microampere. So with this, we can calculate that the length, okay, is actually equals to 0.06 meter. Okay, so in short here, okay, the length, we cannot exceed this point in order to compliant to the class A FCC standard. Next, how can we actually reduce the common mode radiation? Okay, firstly, we must minimize the source voltage, okay, which is the VN. Okay, we need to minimize this as much as possible. Next, we can provide a large common mode impedance in series with the cable or printed track. Okay, imagine if we can have a very large resistance in series with this cable here, okay, then the current will be less reluctant to flow this path, and because of this, then the common mode radiation can be minimized. Okay, shunting the current to ground. So if you put a ground here, this will be minimized the common mode radiation. Last but not least, we provide a shielding. We shield this part here, so nothing can radiate out outside the shield. So we also contain the common mode radiation. With this, I'd like to end my discussion. Please like and subscribe. Thank you so much, guys.